Hello and welcome back to Summer Work Help for Calculus 1. In this video, we're going to be taking a look at question number 19. So for question 19, directions say, graph each exponential function below, indicate any horizontal asymptotes with a dotted line, and plot at least 3 points. Okay. So part A. So for part A, we've got y equals 2 to the x. Okay, so this is a relatively basic exponential function. My base is 2. My input is x. I don't have a vertical shift. I don't have a horizontal shift. So this is sort of what a lot of exponential functions are going to look like. So it says plot at least 3 points. So not a bad idea. If you're not sure where to get started, I guess first of all, the directions don't say that you can't use a calculator. All right. So if you have the TI-84 or Desmos or something like that, you want to get an idea as to what this graph looks like, go right ahead. I do think that there's value in sort of understanding why the graph looks the way that it does. So if you want to use a graphing utility and sort of copy that over, it's not really like the end of the world if you get some help on a question like this. But I'm going to try to do it without using any kind of technology. I just want to sort of like, can I generate this graph? So one way to do that, and not just for exponential functions, but for all functions, is you could just sort of create a table of values. And if you're not sure where to get started, I'm going to list some x values, but I'm going to actually, you know what I'm going to do? I'll start in the middle, I guess. So we'll start with 0. Starting with 0 is generally not a bad idea because it will tell you the y-intercept, right? If it exists. So if the y-intercept exists, when you plug in a 0 for x, the result is your y-intercept. So when you plug a 0 in for x here, you get 2 to the 0. Now, any number to the 0 power other than 0 itself is 1. We saw this way back in question number 1. So when I plug in a 0, I get a 1, so I'm right there. And it says plot at least 3 points, so we might want to sort of indicate what the xy sort of coordinates are, but we'll do that when we're done the entire graph. Okay, so that's it. That's all. There's only one y-intercept, right? Because if there's more than one y-intercept, it's not a function, right? So clearly that's my one and only y-intercept. And then I guess I could see what happens when I go to the right. So when x equals 1, I go ahead and plug that in, and I get 2 to the first. Well, 2 to the first is just 2. So when I plug in a 1, I get a 2 right there. I might as well keep going. When I plug in a 2, I get 2 squared, so 2 times 2, which is 4, which is right there. When I plug in a 3, well, I get 2 to the third power, so that's 2 cubed. So 2 times 2 is 4, times another 2 is 8. So when I plug in a 3, I get an 8. So it's 4, 5, 6, 7, 8, right there. And when I plug in a 4, I'm going to get 16, which is off of the graph. So I can graph the right side of this graph like so. Like that. A little wobbly there at the end, but it's fine. Now I want to see what happens when I go to the left. So if I plug in, like, let's say -1. Well, if I plug in -1, I have 2 to the negative first power. A negative exponent means it's 1 over that thing. So 2 to the -1 means it's 1 over 2, so 1/2. Which is 0.5. So at -1, I get 0.5, which is like right there. At -2, I have 2 to the -2. So 2 to the -2, I'll do this over here briefly. 2 to the -2 is 1 over 2 squared, which is 1 over 4, which is 0.25. So it's like right like there. Okay, so 0.25. -3, well, that's going to be 2 to the -3rd. And by a similar rationale, 2 to the -3rd is 1 over 2 cubed, which is 1 over 8, which is 0.125. So that's like there. So 0.125. All right. Notice that, it's going to get hard to plot these points because you're kind of getting scrunched up onto the x-axis there. But no matter how far to the left you go, if we were to jump to like -10, right? Well, 2 to the -10 is 1 over 2 to the 10th. 2 to the 10th is, I believe, 1024, and then 1 over that is like 0.000 something, right? So what's going to happen as x gets increasingly negative, right? As the magnitude increases, but it becomes a larger negative number, what's going to happen is you're going to get 1 over 2 to some increasingly large positive number, right? And so what's going to happen is your result is going to get closer and closer and closer to 0, but it will never actually hit 0. Because even if it's like x equals -1,000,000, well, now it's 1 over 2 to the million. 2 to the million is some gigantic number, right? Which means 1 over that is going to be really, 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 really small, okay? But it's going to be positive, and it's going to be above 0, right? So this graph is, it's going to go right up against the x-axis there, but it's never actually going to cross it. It's just going to get closer and closer and closer to that x-axis without ever actually crossing it. So the directions do say, plot some points. So, we'll indicate 0, 1. This guy right here is a 2, 4. And I guess we could indicate 3, 8. And this was 1, 2. We're obviously plotting more than just 3 points here. And we'll go ahead and indicate a negative. Why not? -1, 0.5. That's it. And then the directions also say indicate any horizontal asymptotes with a dotted line. So a horizontal asymptote is it's a horizontal line, obviously, that represents a function kind of approaching some value, but never actually really getting to that value as you go like kind of really far to the right or really far to the left. So as x approaches infinity or as x approaches negative infinity. So it's a little difficult to indicate this because it is the x-axis itself. So I'll just try to indicate here that right there, right, the line y equals 0, okay, which is the x-axis, that is my horizontal asymptote for a. And that is my graph of that exponential function, y equals 2 to the x. Notice, just kind of big picture here, as we go to the left, we approach but never actually get y equals 0, okay? And then as we go to the right, notice that our graph like shoots up, right? It points, it's practically pointing straight up at the end there, right? So that's just an example of like exponential growth, okay? Exponential functions that are of this form increase very rapidly as you go to the right. And the reason is because my base here is larger than 1. All right, so because my base is larger than 1, it means that as I go to the right, eventually my graph is going to is going to increase very rapidly. And then as I go to the left, it's going to approach some horizontal asymptote. In this case, it was y equals 0 because there is no vertical shift. If there was a vertical shift of like, 2 to the x and then like plus 5 or something like that, then the horizontal asymptote would be y equals 5. Okay, B. So for B, in some ways, B is very similar to A in that it's just some number to the x power. So again, we don't have a horizontal shift, we don't have a vertical shift, we don't have a stretch. There's no coefficient in front of the 1/2, but it is going to be different in one, maybe two key ways that we're going to see in just a second. Again, if you use a graphing utility here to get the graph and just copy it over, that's better than nothing, but it is also a good idea to just sort of have an understanding as to sort of why the graph behaves the way that it does. We'll make a table, I guess, here. We may end up erasing this table when we get to C, but for right now, it's fine. All right. Maybe you have an idea as to what this graph is going to look like. Maybe you don't. Maybe you know where to start. Maybe you don't. If you're ever trying to generate a graph from a table of values, if you're trying to generate the table that's going to give you the graph, and if you don't really know where to start, you can always kind of start at 0 and sort of see what happens. Depending on your graph, starting at 0 might not be a good idea. But for this one, there's no shift, there's no stretch, so we'll just see what happens when you plug in a 0. So when you plug in a 0, you end up getting 1/2 to the 0 power. Well, again, any number other than 0, if you raise it to the 0 power, gets you 1. So when you plug in a 0, you get a 1, which is actually exactly what we got for A. Again, maybe you know where to go, maybe you don't. So you could see what happens when x equals 1. And just kind of see what happens. So when x equals 1, you've got 1/2 to the first power. Well, anything to the first power is just itself. So this is just 1/2, and 1/2 is a decimal 0.5. You could leave it as 1/2, but the fractions are going to get kind of complicated. So I would recommend looking at decimals here. So when you plug in a 1, you get a 0.5. So that's about there. When you plug in a 2, well, 2 gives you 1/2 squared. So 1/2 squared, you could either distribute the 2 to both the numerator and denominator, or convert the fraction to a decimal and then raise the decimal to the second power. No matter what you do, you basically get 1/4, which is 0.25. So however you simplify that, you should get 0.25 as a decimal, which is 1/4. So at 2, you get 0.25, which is closer to 0. And you can probably see what's going to start happening here. When you plug in a 3, you get 1/2 to the third power. So that's 1/2 times 1/2 times 1/2. Also, of in mathematics basically means multiply. Well, not in all contexts, like not like f of x, but like if you're talking about like 40% of 10 or whatever, then you're multiplying those numbers together, right? So this is 1/2 of 1/2 of 1/2. So that's 1/8, which is 0.125. So that's like there. So you can kind of see what's happening here. It's sort of like the mirror image of A, in that what's going to end up happening is as x gets larger, as x goes to the right, you're going to keep raising this fraction to a larger power, and you're going to keep taking half of whatever it was you got before, right? If you go from like x equals 4 to x equals 5, you've added another factor of 1/2. And when you multiply by 1/2, you get a smaller number. So as you go to the right, you keep taking another half, another half, another half, another half, another half. So what's going to happen is your value is going to keep getting smaller and smaller and smaller, but it will never equal 0, and it will never become a negative number. It's always just going to be a smaller and smaller and smaller positive number. So that's what the graph looks like going to the right. And then from 0, if you go to the left, like -1, well, when you have a fraction to a negative number, I'll just do this here. When you have like 1/2 to the -1 like that, well, you can drop the negative and flip the fraction. So if I drop the negative and flip the fraction, this becomes 2 to the 1 to the first. And that's just 2. So when you plug in a -1, you get a 2. So that's right there. When you have a -2, and I'll erase this and we'll do it again. Okay. So when you have a 1/2 raised to the -2 power, well, again, you can drop the negative and flip the fraction. So this is 2 over 1 squared, which is just 2 squared, which is 4. So when you plug in a -2, you get a 4 right there. And then you could probably see that this is going to continue. When you plug in a -3, you've got 1/2 to the negative third power. So you can drop the negative and flip the fraction like this. So it's just 2 to the first cubed, which is 8. So when you plug in a -3, you get an 8, which is right 5, 6, 7, 8, which is right there. And clearly this pattern is going to continue. So at -4, you're going to get 16, which is off of your graph. So we'll stop there with plotting points. And so the graph looks like that. And we can just sort of indicate some of the points that we used. So -3, 8, -2, 4, -1, 2. This was 0, 1. And that's good enough. We'll maybe indicate one more, 1, 0.5. And then also, it says to indicate any horizontal asymptotes. So this actually has the same horizontal asymptote as A. So maybe we should have mixed it up a little bit and added maybe like a vertical shift here, just so it wasn't the same answer, but it's fine. There's a vertical shift in C, so we'll see it in C. So for B, my horizontal asymptote is the same as it was for A, which is it's the x-axis, and the x-axis has an equation of y = 0. And as you can see, the two graphs are the mirror images. It's sort of like if you flip one over the y-axis, you get the other one. And that's not a coincidence. 1/2 is 2 to the -1 power, so that's to be expected that would happen with our graph. Okay, so C. Same directions. We have an exponential function. We want to graph it. So for this graph, we again have a, and sorry, one more thing about B. With B, the reason why the graph looks like this is because my base is between 0 and 1. So because my base is between 0 and 1, we end up getting this kind of an exponential graph, whereas again with A, we had sort of a more typical exponential graph because my base was larger than 1. So just keep in mind that in general, when your base is greater than 1, it looks kind of like A, and when your base is between 0 and 1, it looks kind of like B. If your base is less than 1, it's not an exponential function. So just FYI. All right. C. So for C, we again have an exponential function. Our base is 1.5. Okay. We also have a stretch here of 2, and we have a vertical shift of -10. So a little different. And I'm going to, I would say if you don't know what to do here, you can always kind of rely on generating a table of values to sort of see what happens here. So we'll go with not 0, we'll go with x and y. And I guess we'll go with, we'll start with 0, but because of the shift, we may end up using more positive values than negative values here, but we'll kind of see how far we get. So we'll start with 0. So, this is saying what happens when we plug a 0 into this function. And when you plug a 0 into this function, notice that I get 1.5 to the 0. So 1.5 to the 0 is 1, okay? But then I take that 1 and I multiply by 2, okay? That gives me 2. And then 2 minus 10 is negative 8. So again, I plug in, x becomes 0. So that's 1.5 to the 0, which is 1. 2 times 1 is 2, and 2 minus 10 is negative 8. You want to do that on the calculator, you're welcome to do so. Also, if you're generating a table, and if you have the TI-84 calculator here, you can also go to y equals, type this in, and then bring up a table with second graph. So that could be a handy way to kind of generate the table as well. Let's go to the right. Okay, so 0, negative 8. So 1, 2, 3, 4, 5, 6, 7, 8. So I'm right here. Okay. I'm going to hold off on indicating that on my graph until I sort of know what the rest of the graph looks like. So let's go to the right first and sort of see what happens. 1. So when I plug in a 1, I get 1.5 to the first, which is just 1.5. Then 1.5 times 2, 1.5 is 3 halves. So multiply by 2 and you get 3. And then 3 minus 10 is negative 7. And again, you want to use a calculator to figure that out. That's, not a bad idea. So at 1, you get negative 7, which is right there. Okay. Then we get a 2. So when you plug in a 2, you get 1.5 squared. Okay, this is where, if you haven't been using a calculator yet, this is probably where you might want to use it, either just straight up like on the home screen, or again, you can always generate a table by typing this into y equals and then bringing up the table, okay? So, and that's okay, it can save you some time. So when you plug a 2 into this, you get negative 5.5. I'm going to list out a few more here. Oh, so negative, let's actually plot that. So at 2, you get negative 5.5. So 1, 2, 3, 4, 5. 0.5 is right there. When you plug in a 3, you get negative 3.25. So negative 3, 1, 2, 3, and some change, and you're right about there. 4, you're actually positive, just barely. So 4 is just barely above the x-axis at 0.125. So now we're right there. At 5, you get approximately 5.2, like that. It's like 5.1875, yada, yada, yada. So at 5, you get about 5.2. So 1, 2, 3, 4, 5, we're right there. And at 6, we get 12 and some change. So let's see, is that going to fit? That's 5, 6, 7, 8, 9, 10. It's going to be just barely out of the graph. So it's going to be like right there. All right. Going to the left from 0, negative 1. When you plug in a negative 1, again, this gets a little tricky with the decimal, so I would just use your calculator here to figure it out. You get negative 8.6 repeating. So that's more negative than it was at 0. So it's going to be farther down. So at negative 1, you're like right about there. At negative 2, you get negative 9.1 repeating. So at negative 2, you're just barely below 9, which is right there. At negative 3, you get about negative 9.4 something, something, something. So at negative 3, we're at right about there. And you can hopefully kind of see what's going to happen here, which is let me fill in the right portion first. So that looks like this. Okay. Now, we're going to want to indicate where our horizontal asymptote is. Well, notice that in both A and B, for A, it was when we went to the left, and for B, it was when we went to the right. Notice that we were approaching 0, okay? But that was when there was no vertical shift. With C, we have a vertical shift down 10. So what's going to end up happening is the first part here, this part right here, this is going to approach 0, right? As x gets closer to negative infinity. And this is kind of like a limit, and we're going to be talking about limits in class. But this is basically just saying that as you go to the left, that first part there, as x gets increasingly negative, it's going to get smaller and smaller and smaller and smaller, and it's going to get closer and closer and closer to 0, although it will actually never get to 0. No matter how far to the left you go, that first part will never actually equal 0. And then what's going to happen is you're going to take that very, very, very small number and you're going to subtract 10 from it. So just like the first two, you never went below 0. This graph is never going to go below negative 10, which is right here. Okay, this graph is 12 by 12 by 12 by 12. So my horizontal asymptote here is located at y equals negative 10, because the first part will never go below 0, and when you subtract 10 from that, it'll never go below negative 10. So that's my horizontal asymptote. So my graph gets really, really close to that horizontal line, but never really touches it. So that is my graph. And it said to plot 3 points. So, plotting your y-intercept is normally a good idea. So this was 0, negative 8. We also plotted 1, negative 7. We plotted 3, negative 3.25. I would say that, the points that you plot should be exact. So like at negative 3, we got like negative 9.4 something, but like it wasn't exact. And then at 5, we got 5.2. So it just said to plot 3 points. I'm going to go with those 3 points. Actually, I guess we skipped 2. That's kind of strange. So 2 was at negative 5.5. That's enough. I say we stop there. Otherwise, we're just kind of cluttering up the place. So that is my graph. I graphed my at least 3 points, and I graphed my horizontal asymptote, and that is what the graph of my exponential function looks like. So this graph had a base of a base larger than 1. That's why it tails off to the left and then increases on the right. It had a stretch of 2. All right, so that's just adding another kind of vertical element to this, and then it had a vertical stretch down 10 units. And then that is that graph. So all 3 graphs for question 19.